Welcome back. Okay, so those were some of the principles that underlie good design, and if you want to be a competent designer, you have to understand those principles. But it doesn't follow from that that you have to solve every problem from such first principles. Okay, so the idea behind design patterns is that they capture good but non-obvious solutions to common problems that are tricky in the context of object orientation. So good, obviously, there's no point in capturing a solution if it's not a good solution. We're trying to help people to learn good solutions. And non-obvious, because if we're going to go to the trouble of writing down a design pattern and teaching it to people, it had better not be the kind of thing that everybody's going to think of when they just apply some basic principles in an obvious way. Now, design patterns arose in the context of object orientation, but that doesn't mean that they're actually in any important way specific to object orientation as a concept. Okay, it would be perfectly possible for functional programming to have patterns as well. They'd be different ones. Okay, they would capture things that are obvious in object orientation but tricky in functional programming. And so you'll sometimes come across people saying, oh, those design patterns, they're just stuff that the object-oriented people need because they're too silly to use functional programming, and if only you used functional programming languages you wouldn't need these patterns because it would be obvious, it would be easy. Okay, and that might be true in the case of particular patterns, but it would completely miss the point because there are different things that are easy in OO and hard in FP. Okay, now because these things are good, they can often, if you have the right problem, solve the problem, and that's useful. But typically the fact that they're not obvious solutions tends to go along with the fact that they also kind of add complexity to your design. So it's quite important to avoid applying design patterns in a blind way. You certainly don't want to say, oh look, here is a place where I could apply, I don't know, observer. Okay, you only want to use a particular pattern if you really have the problem that the pattern is trying to solve. Okay, so design patterns are reuse of good ideas. Here's my favourite one-sentence definition of a pattern. A pattern is a named, well-understood, good solution to a common problem in context. Okay, and we'll see how each of those elements appears in what it is to be a design pattern. But fundamentally what's going on is the observation that experienced designers, part of what it is to be an experienced designer, is to start to recognise the kinds of problems that occur again and again, and part of the expertise is that you start to understand how to solve them. And the idea is that patterns help novices to learn, by the example embodied in the pattern, to behave more like the experts, in a faster way than having to learn from your own experience and your own mistakes. However, it turns out that patterns do several other things, and in fact this teaching novices may not even be the most important thing that patterns do, so we might come back to that. Probably not in this lecture, I think in the next one. So fundamentally the idea of patterns comes from architecture, building architecture. An architect called Christopher Alexander is actually now much more famous through being the originator of the idea of patterns, which took off and became very popular in software design, than he is as a building architect. You can try this out by going and asking people you know who are software designers and people you know who are architects, if you happen to know anybody, whether they've ever heard of Christopher Alexander, and I think you'll find that the software designers are much more likely than the building architects to have heard of him. But he wrote some very nice books capturing common problems and their common solutions in architecture, and one example is a thing he called window place, and the observation is people need comfortable places to sit in a room and they like being near windows, and so a well-designed comfortable room to be in will often turn out to have a comfortable seating place that's placed at a window, okay, because people tend to like that. Okay, otherwise they start kind of pulling the furniture around and wishing they could sit by the window and that kind of stuff. And similarly there are lots of commonly arising technical problems in software design. Part of the value of patterns comes from the fact that you can have pattern catalogues, So you can have the patterns written down in a standard format for easy reference. And at the same time, having your named collection of patterns allows designers to talk shorthand, because instead of saying, why don't we use this solution I've seen before where you have one of these classes and one of those and a dependency like this, you can just say, why don't we use observer, or why don't we use state? And provided that you are in a group of people who are all familiar with those standard named solutions, you don't need to say any more. They know what you mean when you propose using a particular well understood pattern, and that can save you time in your design discussions. And then pattern languages are a bit more than just a catalogue of patterns, because they start to capture the ways in which patterns are related and so on. We'll come back to that a little bit at the end. Patterns have been tremendously popular. They're maybe not quite as popular an idea in research as they were a decade or so ago, but they've been used in re-engineering, in project management, in configuration management and so on. So it's an idea about how you can write down expertise and have a standardized way in which to refer to it, which incorporates giving each chunk of expertise a name so that it can be referred to in discussion. Part of what a pattern catalogue is a standard way of writing down a pattern, which means it's going to have a standard collection of elements. And here's a fairly typical one. It's certainly going to have a name. It might also have some aliases, because we're talking about common design solutions, the kind of things that experts all know. It can easily happen that the same pattern ends up being known by different names. And so that's important to record when that happens. We'll have some kind of context, which basically says this is a short section which lets you say what circumstances are we talking about where this kind of problem arises. And the idea is that is the thing you read skimmingly when you want to say, well, is it worth me reading the rest of this pattern? Is it possible that I've actually got the kind of problem that this pattern is addressing? Then you explain what the problem is, and part of that is to explain why you can't just use the naive design in the particular context that you're talking about. What problem will you run into if you just do the obvious thing? Then you give a solution, you explain what this good design chunk is, and that will normally be a mixture of explanatory text and some models, some UML diagrams or whatever it might be, maybe some pseudocode or some actual program code. And then, very importantly, there will be some kind of discussion section, maybe it's called consequences, which basically says these are the good and bad things to watch out for if you use the pattern. So it's not only this is why you should use it, it's also stuff like these are maybe the competing solutions that you might want to consider because they might actually be better in your context, or these are the gotchas, this is a good solution but sometimes it can get you into this set of problems and you want to watch out for that. All the stuff that you might otherwise wish you had known later on. And there are different formats for different pattern catalogues, and it's worth picking up some of them in a bookshop and having a look. And there's some required reading, and you can have a look at web pages that give pattern catalogue entries as well. Time for an example. So this is a bit of a hoary classic example. Suppose that we have some kind of graphics application, and that it's going to work with some primitive graphic elements like lines, text strings, circles, and so on. And so a client of this application is going to interact with these objects in a kind of a uniform way. So it might, for example, expect to be able to instruct each of these things, lines and circles and so on, to draw themselves, to move, to change colour, and what have you. So you're going to say, well, obviously, I'm going to want some kind of an interface or an abstract base class, perhaps we'll call it graphics, which describes those common things that all graphics elements have, the set of messages that it is possible to send to any graphics element. Okay? And then you're going to have some subclasses or some implementing classes, text, line, and so on. Good, fine. The next thing that comes along is to say, we also want to be able to group elements together to form pictures which can then be treated as a whole, and we want to be able to do the same things with those pictures. So we might also want to be able to to move a composite picture just in the same way they move primitive elements. Our clients might expect to be able to interact with the composite pictures without needing to care about whether this is a composite or a primitive. This is the idea. Now it might be that the collection of primitive elements and the kinds of grouping that are available might have to change relatively frequently as the program evolves, and so we might want to ensure that clients won't have to change every time one of those things changes. So here's the kind of naive solution that you might come up with, and you might think of this as the kind of Friday afternoon solution. You're not going to put a lot of thought into it, you're just going to say, I just want something that's going to work in a basic kind of way, so I can go home. We could create a new class, say container, which contains a collection of graphics elements. And then we say, well, we have to rewrite all the clients, but we've only got to do it once. Okay. So the clients are now going to know about the primitive elements with their common interface, and they're also going to know about containers. Okay. So they're going to have a variable of each type and some kind of Boolean flag to tell them which they're using. And then when they want to, I don't know, to draw the thing they're looking at, they're first going to check the flag to say, is it the case that this thing is container? And if it is container, then they're going to ask the container for its collection of children, and then having got its collection of children, then they're going to send the message to each child in turn. And if it's not a container, then they're just going to do what they would have done earlier. They're just going to send the message to the simple graphics object. Okay, well that kind of works at the expense of having to rewrite all the clients. The other problem with it is that it's not very flexible, because we've allowed for containers to exist containing primitive graphic elements, but the next thing your customer's going to turn around and ask you for is to treat containers just like graphics elements, in the sense that containers can contain other containers, because that's an obvious thing to want, and you haven't got it. Okay, you're now going to have to go on and complicate your solution even more. So that won't do. This is a situation which is worth thinking about because it's really quite common. It often happens that we want to model tree-like structures of objects, where an object might be a thing which is primitive, doesn't have interesting structure, it's a leaf of the tree, or it might itself be composed of other objects, which in turn might be leaves or might be composed of other objects. Okay, so this is a problem that arises relatively frequently, and it's worth having a good solution to. Okay. And what we would like is clients, other parts of the program, to be able to interact with a single class and not have to care about the structure of the tree. And Composite is a design pattern which describes a well understood way of doing it. And its UML diagram looks like this. Now, if we look at the left-hand side of the picture first of all, so far so unsurprising. We've got line, circle and text, and they all inherit from the abstract class graphic, just as we said at the very beginning. And if we now look just at the right-hand side of the picture, we've now got something that's also relatively unsurprising. We've got a picture which contains some graphics of whatever kind, and in order to implement the drawing method of picture, we're going to iterate over our children, our graphic pictures, and we're going to send each of them the draw message. Now, what is worth noticing is that we've kind of turned the naive solution inside out. Instead of having all the clients have to get hold of all the graphics that were contained in the picture and send them each the message in turn, we're saying, well, the picture will be responsible for doing that. We'll allow the picture itself to implement the draw message, and what it will do on receipt of the draw message is to get its children and send them each in turn the draw message. Okay? And the beauty of it is that by making the picture itself implement that interface graphic, or inherit from that abstract class graphic rather, as is shown here, that means that a picture is a graphic just like a line is a graphic, and it's that which allows us to treat pictures exactly like any other graphic, because they just are. And so just as a picture can contain a line as one of its children, there's nothing to stop a picture containing a picture as one of its children. Okay. Now, you might start to worry about infinite extents of objects here. Of course, in an actual case where you've got a real tree of objects, everything's going to have to bottom out at primitive graphic elements eventually. Okay, otherwise you just wouldn't be able to construct the picture. And in fact, if you think about how you would implement this, how you would write the constructor, that will kind of fall out quite naturally, because what you'll expect is to be able to say, well, in order to construct a picture, I've probably got a constructor which takes some graphics as arguments, and I'm not going to be able to invoke that constructor until I've built some graphics, and so on. So we'll get it will work inductively. So the benefits of composite are that we can automatically have trees of any depth. We don't need to do anything special to let containers, pictures in this case, contain other containers. And the clients can be kept simple. They only have to know about the graphic class and its interface, the messages that they can send it, and they never have to worry about recursing down the tree structure themselves. And of course, it's easy to add new kinds of graphic subclasses, including, by the way, different kinds of pictures, okay? Because clients don't have to be altered, they're just interacting with the graphic class. Drawbacks, there are always some drawbacks. Supposing you actually wanted to write clients which only worked on primitive graphics elements, it's now not easy to do that because we've hidden that information. Okay? We've made sure that a picture is no more different from a line than a circle is, from the point of view of the type checker. And maybe you might want to think about some kind of halfway house solutions where clients are allowed to know about whether they're dealing with a composite object if they wish to. And that's the kind of refinement to a pattern that is quite often useful to think about. The trick is to keep sight of what it is you're trying to get from the pattern so that you don't end up just kind of undoing the pattern design because you're actually in a situation where the pattern wasn't useful to you anyway. So, if you want to know more about patterns, the two best known pattern collections are these two at the top, the so-called Gang of Four book, GOF book, Design Patterns, Elements of Reusable Object-Oriented Software. This was the original one that brought patterns to prominence in the object-oriented design community by Gamma, Helm, and Johnson and Vlasides. And the so-called POSA book, A System of Patterns, Pattern Object-Oriented Software Architecture by Bushman et al. And there's a whole bunch of other books. Those are just a two that I like. Pattern Hatching is a very nice small book, which is very thought-provoking as an explanation of how to use the GOF patterns and how to use the GOF book. So you might like to have a look at that one. And there are events and conferences and what have you, although not quite as many as there used to be a few years ago. We're going to talk through a few patterns, mostly next time, but I rejected the idea of trying to put full information about patterns on slides. If you want to seriously use patterns, you will need a copy of the Gang of Four book. For exam purposes, slides plus the required reading references will suffice. Okay, and I'll show you later on that there are specific patterns I expect you to know for exam purposes, and there's a list in the next set of slides. There's lots of information online. The Wikipedia articles on each pattern are often useful, and there are some more links on Learn. And there are lots of code examples in the Wikipedia articles. You can get bogged down in it, and sometimes there are very amusing arguments on the talk pages of these things, and sometimes those can be actually just as informative as anything else. If you like reading arguments between people as a way of learning, look at those talk pages. A few bits of patterns jargon that I want you to have met. Forces, quan, generativity, and rule of three, just very quickly at the end. So, forces is the idea that the reason why design problems are hard in the first place is that they typically involve potentially conflicting priorities or forces. So, for example, you want your system to be easy to extend, which might push you towards saying, I'll have an abstract superclass for this class I just invented, just in case I ever want to make a variant of it. But also you want your system to be small and simple without having more classes than you really need to have in your system. That might push you away from that solution. Okay, and so balancing that is all about saying, well, I'm going to include an abstract superclass if and only if there's a reasonable chance that I actually will want several different implementations of it, and not just for every class just in case. Okay, so this is kind of design sense, really. Some pattern writers like to make the forces explicit in their pattern writing. Okay, and forces come from the problem. So there's no design pattern which is always the right answer in any given technical situation. It's going to depend on the business environment in which your software system is living. And very often it's about which things might have to change. Patterns are very often about making it possible to change things relatively easily, at the cost of some complication of the design up front. It's only worth incurring that complication of the design up front if there's a reasonable chance that the thing it will allow you to change more easily actually is going to need to be changed in future. And that's about understanding which elements of the domain in which your software system is sitting are stable and which are unstable and likely to have to change in future. And so this is all, design is still a judgment. Quan is the quality without a name, and Alexander himself introduced this in The Timeless Way of Building, which is one of his books. And it means something like wholeness or vitality or integrity. It's about when a design feels good, basically feels as though it's consistent. Okay. Generativity is another term that Alexander introduced. There are two senses in which patterns can be considered to be generative. The straightforward one is that it tells you how to build something, but the more interesting one is that different patterns, which are used well together, can have good emergent properties. So this is part of what the discussion sections of your pattern catalogue are doing. They are directing you towards patterns that might also be worth considering if you're considering this one, either because this other pattern might give you an alternative solution, or because the kinds of circumstances in which this pattern is useful often turn out to be situations in which this other pattern is also useful. It has been claimed that patterns generate architectures, that it might make sense to look at your software architecture and for each class say which patterns does this class participate in. I think that's probably not really right because of the complication that patterns tend to introduce. I think it's more right to say that most software architectures will typically involve only a few gang of 4 patterns. The rule of 3 is an interesting one because they are the counterweight to a thing which can be a problem, which is to say somebody invents a design solution and they're terribly proud of it and they write it down as a pattern and try to sell it to everybody else to say you should use this too, and sometimes it's not worth writing down because it's so specific to its context in which it arose that it's never going to arise again. You're never going to find another application in which this precise solution is what you want. And so the idea here is that to count as a pattern, a thing should have 3 independent successful uses. And this is partly just to avoid codifying sort of one-off neat ideas, and it's partly to get the description of a pattern at the right level of abstraction. Okay? It's quite difficult to write a pattern to encapsulate a chunk of expertise, even if you have the expertise, because you're struggling between abstracting away so much detail that you write down something which is so high level that it's completely obvious and not worth writing down in the first place, or at the other extreme, writing down so much detail that you've got something where it doesn't apply in enough situations. So the sweet spot is to say where you capture sort of enough essential detail to be able to explain what it is that's clever and important about the pattern, without going into so much detail that most readers will look at it and say, well, that's not the situation I'm in. And the Gang of 4 book actually includes a known uses section where people can write about actual successful uses of a pattern, which is often quite an interesting thing to look at. Ways in which patterns are useful. I started off talking about teaching novices to behave more like experts, and that was certainly how software design patterns were originally conceived. That was the original advertised use of them. But actually it turns out that high-level vocabulary, that ability to use the names of patterns, like composite for example, in design discussions, is at least as important. The other thing which is very useful is reading pattern descriptions as a way to practice your general design skills. So if you read a description of a pattern and go through the process of understanding why this is a good solution, under what circumstances this is a good solution, that's a very good way to kind of build up your design muscles and your design understanding. Sometimes they are useful as an authority to appeal to. If somebody doesn't believe your design could possibly work, then being able to point at the entry in the pattern catalogue where it says this is a respectable design can be useful. And sometimes teams and organisations even like to write down their own patterns, just as a convenient cataloguing way of how we do things around here. I'm not going to say any more about that, I don't think. You do have to be cautious, and I've already said this in passing, I think, in that they add complexity and sometimes other things like performance penalties as well. So you only want to incur the cost of that extra complexity if you actually are going to benefit from the use of the pattern. In other words, if you have the problem that the pattern is trying to solve. And I also said at the beginning that you may encounter the criticism that the Gang of Four patterns are just getting around the deficiencies of object orientation. It's kind of true in the sense that what many of them are doing is taking a problem which wouldn't be a problem if you were writing in, say, functional programming, and explaining how to solve it in object orientation. But whatever paradigm you write in, there are going to be some things which are easy and other things which are not easy, and the purposes of patterns is to help you to do the things which are not easy. You could perfectly well have a pattern language for your favourite non-OO language, and you might like to incur the challenge of trying to write one, or indeed Google to see whether anybody has yet. I haven't done that recently. And that's all I want to say about patterns for now.